We're going to take a few moments to talk about ionic compounds. Remember that an ionic compound is a compound that is formed from two or more elements that have greatly differing electronegativity values. And you can find those electronegativity values by looking at an electronegativity chart. Often we think of, since it's great electronegativity differences, that we're dealing with different parts of the periodic table. So quite often we think of them as the metals and the nonmetals bonding. However, we know that we'll find instances where that bond is going to be more polar covalent than a pure ionic bond. So let's talk about these ionic compounds. Let's say we've got our easiest one to deal with, sodium chloride. So I have Na1 plus ions in a 3D crystalline structure with Cl1 negative ions. And so they just organize themselves in 3D, and I can't really do that on my little computer here, but I am going to put a few on here so we can kind of see what we're doing. They form a nice pattern, and their pattern is due to electrostatic forces that are holding them together. We've got positives and negatives, kind of like a magnet, electrostatic forces holding them together in this 3D. So imagine this is going back. It's a chunk of salt. It's going back in 3 dimensions, and we've got it all nice and neatly organized. Now, if we wanted to make it conduct electricity or anything like that, it's not going to in the regular solid form. If I put 2 electrodes up to a chunk of salt, I'm not going to get it to conduct electricity. But the moment that I start heating this up, so I've got a Bunsen burner under here. I heat it up really hot because salts have really high melting points because those electrostatic forces are so strong. If I heat it up enough, it's going to become molten, which means I'm going from the solid to the liquid state. And as I'm doing that, my molecules end up moving more back and forth, and so there's more movement within them. And when that's the case, then I can start putting electricity through them because they're kind of moving and not, those electrostatic forces are not held as tightly because they're not as close together in their movement. And so they end up losing that extra electrostatic forces, and so it would become conductive. And now let's talk about if it's aqueous. So we know that salts are water soluble or aqueous, AQ for short. And that's because when I take this chunk of water, let's say we're not using it with a Bunsen burner anymore. Let's say I'm going to put it into a beaker of water. This beaker of water has covalent molecules mixed throughout, but we also know that these covalent molecules have strong electronegativity values, and it's called hydrogen bonding that goes on between the molecules, so between the positively charged hydrogen and the negatively charged oxygen. So partial positive for each of the hydrogens, partial negative for all of the oxygens. There's a force called hydrogen bonding between them that's going to keep them all in this beaker. Now I throw this chunk of salt into it, and these partial positives and partial negatives are going to start breaking apart the positives and the negatives of this crystalline structure because the electrostatic force, that strong attraction from the water, is going to be able to pull it apart. The water is a polar molecule. We don't want to forget that. And so we're going to break up this ionic lattice with the partial positives breaking those Cl's apart, and these partial positives going with the oxygens. And so I end up with a beaker now that's full of ions of Na1 pluses, Cl1 negatives, and a whole bunch of molecules of water as well, with the oxygens being near to the positives of the sodiums, and the hydrogens, which are partially positive, being closer to the negative chlorine ions, and that breaks it apart. Now let's say I had a nonpolar compound, so a covalent, like a pure covalent compound. That's not going to be able to get pulled apart by these polar molecules because different forces are going on with those. The attraction between those nonpolar molecules are not very significant, and so the intermolecular forces of this hydrogen bonding wouldn't be able to pull them apart.